Welcome back. In this lecture video, we're going to be looking at making inferences about proportions in the context of stratified random sampling. Now we'll start off by looking at inference for the individual strata proportions. So recall that we denoted the members of the population, and in particular the response variable that is being measured on the members, by U sub ij. Now, in this context, let's suppose that the uij's are indicator variables, with U sub ij being equal to 1 if the ith member of stratum J has the characteristic of interest, and U sub ij is equal to 0 if the ith member of the jth stratum does not have the characteristic. Then, if we add all of those indicator variables up for the members of the jth stratum, that gives us tau sub j. So tau sub j is the sum of the indicator variables within the jth population stratum. And what that value is, or represents, is the number of members in stratum J that have the characteristic of interest. With that, we can then look at mu sub j, which is notation that represents the mean of that particular stratum. All right, so it still has that interpretation as a mean. Okay, and so it's equal to tau sub j over cap n sub j. In other words, it is the number of members in stratum J that have the characteristic of interest divided by the total number of members in that stratum. And so that quantity, which again is mu sub ij, it is that stratum mean, but it's a mean of indicator variables, and what that gives us then is the proportion of members in stratum J that have the characteristic of interest. And so thinking about it this way, presenting it this way, using this familiar notation is going to allow us to come up with a procedure for making inferences about the strata proportions using what we've already learned about how to make inferences about the strata means. Now let P sub j denote the proportion of members in stratum J that have the characteristic of interest. Then from the previous slide, we know then that P sub j is equal to mu sub j. So we'll just kind of convert now to this notation involving P sub j because it's easier to remember, a little bit more descriptive. It reminds us that we're talking about a proportion. Now, denote the variance of stratum J with respect to this set of indicators. Denote the variance of stratum J by sigma squared sub j, as we have been doing. All right, so that represents the variance of the indicator variables in stratum J. Then it can be shown that sigma squared sub j, is related to P sub j, right, the proportion of members in stratum J that have the characteristic of interest. The stratum variance is related to the stratum proportion by this formula. Sigma squared sub j is equal to P sub j times 1 minus P sub j. Now, I'm not going to prove that. We'll just take that as given. All right, but this shows us that we can express this stratum variance in terms of the stratum proportion. Now, let's think about sampling from the population strata. So as before, let y sub 1j, y sub 2j, and so forth up to y sub nj comma j denote a simple random sample of size n sub j from stratum J of the population. Now remember, in stratified random sampling, what we're doing is selecting simple random samples from each of the various population strata, and those samples are selected in such a way that they are independent of each other. So we have this simple random sample, and it's a simple random sample of indicators from stratum J. Then the sample mean, which is, we've been using the notation y bar sub j. All right, so that's the mean of that sample of indicators. That's equal to P hat sub j, where P hat sub j is the proportion in the sample that have the characteristic of interest. All right, and the sample variance, all right, which in previous part of the notes in the previous lecture videos. Up to this point, let's put it that way, up to this point we've been denoting the sample variance for the jth stratum as s squared sub j. All right, and so we could calculate that in the usual way using this formula here, but the point we're making here is that it can be shown that this is can also be written this way in terms of the size of the sample and the sample proportion. So we've seen that the stratum variance can be written in terms of the actual stratum proportion, and we see here that the sample variance can be written in terms of the sample proportion. All right, now with that, it turns out that p hat sub j, the sample proportion, is an unbiased estimator of the jth stratum proportion p sub j. In addition, an unbiased estimator of the jth stratum variance, sigma squared sub j, all right, so an estimator of that is given by this formulation here, and I'm going to denote the estimate of sigma squared sub j by sigma hat squared sub j. And so this is related to, as we can see here, what we identified on the previous page as the sample variance expressed in terms of the sample proportion. All right, and then we've got this multiplicative factor out here in front that involves the size of the stratum. All right, so p hat sub j is an unbiased estimator of p sub j, and sigma hat squared sub j is an unbiased estimator of the stratum variance of sigma squared sub j. Now, we need to come up with an expression, or the formulation, of the variance of p hat sub j, the estimate of p sub j. All right, so that's given by this formula here. All right, so we see the form of the expression. So sigma squared sub p hat sub j, so the variance of p hat sub j is given by this quantity here. Right, and then we take the standard deviation, or the square root of that, to get the standard deviation of p hat sub j. All right, but again, both of these involve p sub j, which is unknown. That's the object about which we are wanting to draw inferences. All right, so we're not able to calculate the variance nor the standard error of p hat sub j, because to do so would require knowing what p sub j is equal to. So we can't do that. So again, what we need to do is we need to estimate these quantities from the data. That's going to involve estimating the p sub j's, which we've already done. We know an unbiased estimator of p sub j. It's the sample proportion. And so when we plug the sample portion in, that unbiased estimator of p sub j, then we get an unbiased estimator of the variance of p hat sub j. And then when we take the square root of that, we get an estimator of the standard error of p hat sub j. So once we have the estimated standard error of p hat sub j, we can multiply that by 2 to get the estimated approximate 95% margin of error associated with p hat sub j. All right, and so that is given by this expression here. All right, then we subtract that quantity from p hat sub j to get the lower endpoint of the confidence interval. We add that margin of error to the point estimate to get the upper confidence limit. All right, and so that is expressed here on the bottom of slide 56. All right, so this is how we can estimate, with a point estimate and also a confidence interval estimate, the stratum proportions. So now what we want to do is look at how to draw inferences about the overall population proportion, and that's going to involve utilizing what we've just learned, and we know how to calculate now, involving the estimating the individual stratum proportions. So let's first talk about coming up with a point estimate for the overall population proportion. All right, and so the overall population proportion would be denoted by P. All right, that would be the proportion of the members in the population that have the characteristic of interest. And so an unbiased estimator of this overall population proportion is given by this weighted average of the estimates of the individual strata proportions. So this estimator is a weighted average of the individual strata sample means, with the weights being the proportions of the overall sample size within the strata, right? So we see here that cap n sub j over cap n is the proportion of the overall population size within a particular stratum. Then we need to know something about the form of the variance of that estimator. All right, and it turns out that it involves the individual stratum variances of the strata proportion estimates. All right, so the variance of the sampling distribution of p hat is given by this expression. Okay, we take the square root of that to get the estimated standard error of p hat. And then once we have that, well, we can't calculate it, can we? Because we don't know p sub j. All right, so we have to estimate these things. And so that's when we plug in the p hat sub j's. We get the estimated variance of p hat. We take the square root of that to get the estimated standard error of p hat. And so this is what we're after, right? We're after the estimated standard error of p hat. And once we have that, then we can multiply it by 2, all right, to come up with the approximate 95% margin of error associated with p hat. And then once we have that, then again we can start off at that point estimate, p hat, and then go a distance to the left and to the right to get the endpoints of the confidence interval, an approximate 95% confidence interval, and that distance we go is that estimated approximate 95% margin of error. And so this gives us the lower and upper endpoints for that confidence interval. So let's look at an example. Continuing with the advertising example, the advertising firm wanted to estimate the proportion of households in the county that watch a particular show, let's call it show X. A stratified random sample was selected, with N1 equal to 20 households selected in town A, and N2 equal to 8 households selected in town B, and N3 equal to 12 households selected from the rural community. Interviews were conducted and the following results were obtained. 16 of the households selected from town A watched the show, 2 of the households selected from town B watched the show, and 6 of the households selected from the rural area watched the show. For each stratum, estimate the proportion of households that watch show X, compute the margin of error associated with each estimate, and construct an approximate 95% confidence interval estimate of the proportion, so that's within each of the strata. The next question, are there differences across the strata in the proportion of households that watch the show? Evaluate the evidence. And then finally, use these data to estimate the proportion of households across the entire county that watch the show. Compute the margin of error associated with this estimate, and then construct an approximate 95% confidence interval estimate of that overall proportion. Okay, so here we have the information. We have the stratum sizes, we have the sample sizes from the various strata, and then we have the number of households within each of the samples that actually watch the show, and I'm calling those quantities X sub j. All right, and so we'll first do our analysis for each of the strata. And so for stratum 1, the point estimate of P1, which is denoted by P hat sub 1, is equal to X1 over N1. X1 is equal to the number of households in that town, town A, that watch the show. N1 is the sample size. We have 16 over 20, and so that's 0.8. And so our estimate of the proportion of households in town A that watch the show is 0.8. We then need the estimated standard error of P hat sub 1, and so we use the formula and we get 0.08564. Now once we have that, we can multiply it by 2 to get the estimated approximate 95% margin of error of P1 hat. All right, and so that turns out to be, rounding to 3 decimal places, 0.171. Now once I have the point estimate of 0.8 and the approximate 95% margin of error, I can very easily construct the approximate 95% confidence interval estimate of P1. which ranges from 0.629 up to 0.971. And so then what we would say is that we are approximately 95% confident that the true proportion of households in town A that watch the TV show is somewhere between 0.629 and 0.971. Now, I would just point out that that's a fairly large interval, but and that's based on, in large part, the sample size. Right? We don't have a really large sample. Now let's look at stratum 2, the point estimate of P2, P2 being the proportion of households in town B that watch the show. That point estimate is denoted by P hat sub 2. It's equal to X2 over N2, so it's 2 over 8 or 0.25. And so our point estimate for the proportion of households in town B that watch the show is 0.25. The estimated standard error of P hat sub 2 is 0.1527. Multiplying that by 2, we get the estimated approximate 95% margin of error of P hat sub 2. And rounding to 3 decimal places, that is equal to 0.305. And then finally, we can subtract that from and add that to the point estimate, P hat sub 2, to get the lower and upper endpoints for the confidence interval. And we see here that the lower endpoint is negative 0.055 and the upper endpoint is 0.555. Now, we know that proportions have to be between 0 and 1. And so we can go ahead, we can cut the interval off at 0. We don't need to actually extend down to a negative 0.055 because we know that we cannot have proportions less than 0. So we would truncate that at 0. So we have an approximate 95% confidence interval estimate of P2 that ranges from 0 up to 0.555. Again, a very large, wide interval, not very precise at all. But again, that's because of the sample size. We only have 8 observations. We only sampled 8 households in this sample. And then finally, we do the same thing for stratum 3. P3 is the proportion of households in the rural area that watch the show. There were 6 households in the sample of size 12 that watched the show, and so the point estimate of P3 would be 0.5. The standard error of this estimate is 0.1407. That's the estimated standard error. And then the estimated approximate 95% margin of error of P hat sub 3 is twice that, or 0.2814. All right, and so when we subtract that from and add that to P hat sub 3, we get the lower and upper endpoints for the confidence interval, which ranges from 0.219 up to 0.781. Okay, so summarizing those results, putting them all on one page, we have the 3 intervals here. Now, to answer the question, are there differences across the 3 strata in terms of the proportion of households that watch the show? We could go into a little bit more detailed analysis and construct confidence intervals for differences of proportions. Although I'm not going to do that. If you want to do that, that would be a good exercise for you to do. But what I'm going to do is just note that there is overlap between the stratum 2 and stratum 3 in terms of these confidence intervals. All right, but notice that the intervals for stratum 1 and stratum 2 do not overlap. So there appears to be evidence that the proportions are different for town A and town B, but notice that the intervals for stratum 1 and stratum 3 overlap. And so if there are any differences, it would appear to be between town A and town B. Okay, let's continue on and let's construct a point estimate for the overall proportion in the county of households that watch the show. That's going to be a weighted average of the individual stratum sample proportions. All right, and you can see here how we're doing this, and so we get a point estimate of 0.6. And so this represents our best estimate in terms of a single value of the proportion of households in the county that watch the show. So that would be 0.6 or 60%. We then need to calculate the estimated standard error of P hat. And so you can see here it's going to be the square root of 1 over cap n squared times this sum. In this case, because we have 3 strata, right, we're summing over the 3 strata. All right, and you can see here that the calculations are really starting to get fairly long, right, fairly involved. And so we need to be very careful. If we're doing this by hand, right, the more calculations we have to do, the greater the opportunity is. The more opportunities, the greater the potential for an error somewhere along the line. So we really need to be careful with this, and I would highly recommend that you perhaps create a spreadsheet for doing these kind of calculations so that you can make sure that things will be done correctly. Okay, so once we calculate this, we get an estimated standard error of p hat equal to 0.0674. We multiply that then by 2 to get the estimated approximate 95% margin of error associated with p hat. That turns out to be 0.135, rounded to 3 decimal places. And so we get an approximate 95% confidence interval estimate for p, which ranges from 0.465 up to 0.735. Now, this interval is shorter than the individual stratum confidence intervals because we're pooling over more than one stratum, right? We've got a larger sample size here, so we have more information, all right, available to the analysis, and that's reflected in a more precise confidence interval, although it's still somewhat wide, all right, but again, that's a function of the sample sizes. So we can be approximately 95% confident that the proportion of households across the entire county that watch this show is somewhere between 0.465 and 0.735. All right, finally, let's look at inference for the number of members in a stratum with a characteristic. So we're going to be looking at inferences for the total number of members in a stratum and also total number of members in a population that have a characteristic. And so as stated previously, when the mu sub ij's are indicator variables with mu sub I j equal to 1, if the ith member of population j has a characteristic of interest and 0 otherwise, then this tau sub j, which is the sum of the indicator variables for the jth stratum, is the number of members in stratum j that have the characteristic of interest. An unbiased estimator of that total tau sub j is given by the product of cap n sub j, the size of stratum j, and the proportion, the estimated proportion of members in that stratum that have the characteristic of interest. So this is one way that we could get a point estimate for the number of members in the stratum that have the characteristic of interest. Now we need the variance and the standard error, at least the formulas that show us the form of the expression for the variance and standard error of tau hat sub j. And so we have those formulas here, right? And notice that they are in terms of the individual or the stratum proportions. Because we don't know those proportions, if we did, we'd know the total. We'd know the stratum totals. But since we don't know the stratum totals, right, we cannot know the stratum proportions. And so these need to be estimated. All right, so we get those by plugging in the estimates of the strata proportions. Once we do that, we get formulas for the estimators of the variance and standard error of tau hat sub j, and in particular, sigma hat squared sub tau hat sub j is an unbiased estimator of the variance of the sampling distribution of tau hat sub j. We take the square root of this. That gives us the estimated standard error of tau hat sub j. We then multiply that by 2 to get the estimated approximate 95% margin of error that is associated with tau hat sub j. And then once we have that, then we can construct the approximate 95% confidence interval estimate for tau sub j. All right, so let's look at so that's for the individual stratum totals. Now let's put it together, all right, to come up with the procedure for inference for the overall number of members in the population with a characteristic. So the total number of members in a population with a particular characteristic of interest in a population that's been stratified is expressed in terms of the stratum numbers as follows. So tau, the overall total number of members in a population, is equal to the sum of the members from each of the various strata that have that characteristic. An unbiased estimator of tau is denoted by tau hat, and it's given by that expression there. So it's in terms of the stratum sizes and the stratum sample proportion estimates, the p hat sub j's. So that's our point estimator, and now we'd like to know, or at least understand the formula, the form of the expression for the variance of tau hat sub j, and it turns out that that is given by this expression here. All right, so this is the variance of tau hat sub j. This is the true standard error of tau hat sub j when we take the square root of sigma squared sub tau hat, and that gives us the true standard error of tau hat. Obviously, we don't know the p sub j's, and so we have to estimate those in order to be able to come up with an estimate of sigma squared sub tau hat. And so that estimate, denoted by sigma hat squared sub tau hat, is given by this expression here. All right, so we've replaced the p sub j's by their estimates. We then take the square root of that estimated variance to get the estimated standard error of tau hat. Okay, and then once we have that estimated standard error of tau hat, then we can multiply that by 2 to get the estimated approximate 95% margin of error associated with tau hat. And then finally, once we have the point estimate and the margin of error associated with that point estimate, we can subtract the margin of error from the point estimate to get the lower endpoint of that confidence interval, and add the margin of error to that point estimate to get the upper endpoint of that confidence interval. All right, so that is the end of this lecture. So we've looked at how to make inferences about about stratum proportions, and overall, the overall population proportion using a stratified random sample. We've also looked at how to making inferences about a quantity that is related to those proportions, and that is the totals, right? The total number of members in a stratum or in the overall population that have the characteristic of interest. So that wraps up what we're going to be talking about regarding stratified random sampling. We've looked at how to make inferences about means, about proportions, about totals, both in the context of the individual strata, but also across the entire population. We looked at how to determine sample sizes for estimating a population mean. All right, and so that kind of wraps up what we're going to be looking at in the context of stratified random sampling.